Hello everyone, this is Rune Connor. Welcome to part 9 of Me Learning Rust series. The slice type. Okay, slices let you reference a contiguous sequence of elements in a collection rather than the whole collection. A slice is a kind of reference, so it does not have ownership. Okay, so it's a reference, not an object stored in the heap, I guess. There's a small programming problem. Write a function that takes a string of words separated by spaces and returns the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word. So the entire string should be returned. Let's work through how we write the signature of this function without using slices to understand the problem that slices will solve. Okay, let's do that. So function first word. It takes a string reference and returns a question mark. The first word function has a ampersand string as parameter. We don't want ownership, so this is fine. But what should be returned? We don't really have a way to talk about part of a string. However, we could return the index of the end of the word, indicated by a space. Let's try that as shown in listing 4-7. So here it's returning an unsigned integer whose size is determined by your system architecture. That's usize. Okay, let bytes as, so converting the string reference as bytes, representing it, I guess. Don't know what that means. For I ampersand item, this is like unpacking in Python, in bytes, iter for iterator, and enumerate. Okay, and then we're almost there. If item is equal to space character as byte, represented as a byte, return the I index, I guess, coming from the numerator there. What's happening here? Why is this all red? What is this? Not have anything here. Mismatched types. Why? I haven't returned the slen yet. So until I do that, it's gonna just give me red everywhere. Usize found a tuple. Where is that? Oh yeah, it's that thing. Okay, so semicolon does not let you return the value. What is this? It's not used. Okay, let's put it in main. Let's get this code. And let word, first word s. Remove this mute. Does not need to be mutable. Fine. Sure. Intentional, never used code. Okay, so because we need to go through this string element, element by element, and check whether a value is a space, we'll convert our string to an array of bytes using the asBytes method. So it's this thing here that converts this string whose reference we have, I guess. So it takes, so asBytes takes whatever object this S is referring to, and converts that to bytes. Yes. Size 16. Okay. Unsigned at 8-bit, I guess. Next, we create an iterator over the array of bytes using the iter method. That guy. Iterating over the bytes. So byte by byte or character by character. This assumes ASCII, though not UTF-8, which is, I think, 4 bytes in size. And then enumerate just puts indexes in there, creates tuples from the result of this iter. So each character gets an index number, and then at each iteration, the index is stored in this I variable, and the actual character is stored in here. The reference of the character, I guess. Or character as reference. Not really sure still. I'm kind of foggy on the entire references and pointers thing. We'll discuss iterators in more detail in chapter 13. For now, know that iter is a method that returns each element in a collection, and that enumerate wraps the result of iter and returns each element as part of a tuple instead. So this is the tuple that we're getting, right? So index and then the character. This is a bit more convenient than calculating the index ourselves. Right, the first element of the tuple returned from enumerate is the index, and the second element is a reference to the element. A reference to the byte, yes, to the byte here. Because the enumerate method returns a tuple, we can use patterns to destructure that tuple. So this is a pattern, I guess. We'll be discussing patterns more in chapter 6. In the for loop, we specify a pattern that has I for the index in the tuple and ampersand item for the single byte in the tuple. So this thing, because we get a reference to the element from .iter.enumerate, we use ampersand in the pattern. Okay, so .iter returns a reference to the element because of the entire ownership thing. Everything is passed by reference, I guess, in Rust. Otherwise, you know, can't borrow things. I don't know. The ownership transfer mechanisms make things more complicated, I think. Inside the for loop, we search for the byte, and that represents the space by using the byte literal. Okay, syntax. If we find the space, we return the position. So if the byte is a space, return the index of that element. Otherwise, we return the length of the string by using slen, right there. If no spaces are encountered in the string, obviously, you just return the length of the string. So you return the index of the space, right? So that's correct. And here you return the length of the string, which is the index of the last element plus 1. These are the same, basically. Okay, we now have a way to find out the index of the end of the first word in the string. So end of the first word, that's what they're talking about. So the index is the last index plus 1. That's why. But there's a problem. We're returning a usize on its own, but it's only a meaningful number in the context of the ampersand string. So usize that's returned here, it's not a reference to anything, right? It's just a number that's stored in memory and returned by this function. It has its own address and everything, right? So this guy or this guy. That's what they're talking about here. In other words, because it's a separate value from the string, it's a separate object, that is. lives in memory, separate from the string object, there's no guarantee that it will still be valid in the future. When you change the string, that value, the other object that stores this int value, will not change, right? It's going to stay the same. Consider the program in listing 4-8 that uses the first word function from listing 4-7. There. Okay, and then sclear. Let mute s from hello world. Because they use sclear here, that's why string needs to be mutatable. Cannot mutate immutable variables, so that's why they have mute here. Clear method mutates s, changes whatever is there. Okay, I understand now. Okay, so let mute s string from hello world. That's just a mutable string. Let word be the first word of this string. Word will get the value 5. So this function just returns the index of this space character there, which is the number 5, the object 5, which now lives in memory. And this word name is pointing to that object in memory. But when you clear the string, word is still pointing to that object, but the string now contains nothing. Word still has the value 5 here, but there's no more string that we could meaningfully use the value 5 with. Word is now totally invalid, the word variable here. Okay, yeah, that's understandable. This program compiles without any errors and would also do so if we used word after calling sclear. Because word isn't connected to the state of s at all, word still contains the value 5. Yes, exactly. There are two separate objects stored in the heap. They're not connected at all. We could use that value 5 with the variable s to try to extract the first word out, but this would be a bug because the contents of s have changed since we saved 5 in word. Yeah, so later on, if you try and use this somewhere else in the code, connect it to this string, you're going to get a bug. They're trying to prevent that, basically. Having to worry about the index in Word getting out of sync with the data is tedious and error-prone. Managing these indices is even more brittle if we write a second word function. Its signature would have to look like this. Right, second word is getting an ampersand string reference, and returning a tuple of 2 integers. Again, 2 different objects in memory that are tied to the string, but there's no connection between them. Now we're tracking a starting and an ending index, and we have even more values that we calculated from data in a particular state, but aren't tied to that state at all. So you can take this snapshot at some point in the string's life, and later on when the string changes, the snapshot stays the same, basically. That's what they're saying. We have 3 unrelated variables floating around that need to be kept in sync. Yeah, and you would need to remember that as a programmer, which you won't. You'll forget it. Luckily, Rust is a solution to this problem, string slices. A string slice is a reference to part of a string, and it looks like this. Let s assignment make a string from this string literal, hello world. Let hello be a reference to the first 5 elements of the string, these, and then let world be a reference to the elements starting from the 6th index going up to but not including index 11, so these. Okay, so 6, 7, 8, 9, 10. Those are the index values. Rather than a reference to the entire string, hello is a reference to a portion of the string, specified in the extra 0 to 5 bit. Okay, so these guys are a reference to the same object, so they don't create a new object in memory. That's why doing it this way is safer. Otherwise, when you create new objects like this, these integers in memory, you have to manually remember to update them when the string changes as well, which would be a very painful thing to do. But this does it automatically because they're just references to the string, a part of that string. That is, when the string changes, the part of that string is also going to change. Well, if you change the string, you could have different words here. So 0 to 5 would be invalid, maybe different length words, etc. So this is not a very good example either, but it's a good starting example, yes, to show the difference between the reference thing and creating an actual new object in the heap with useSize. We create slices using a range within brackets by specifying starting index, period, period, ending index, where the starting index is the first position in the slice and ending index is one more than the last position in the slice. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to, so the slice data structure stores the starting position and the length of the slice, like this. That's the data structure stored in the stack. The pointer points to the index, the starting index, and you got the length. So it starts at index 6 and goes 5 bytes. Internally, yeah, which corresponds to ending index minus starting index. Okay, so the length of the slice is ending index minus starting index. So in case of let world ampersand S6 to 11, world would be a slice that contains a pointer to the byte at index 6 of S with a length value of 5. Right, just like it's showing here. If it's a string data structure like this, you also have capacity. You don't have that in this one. It's just a reference to the string, to a slice of the string, rather. With Rust's double period range syntax, if you want to start at index 0, you can drop the value before the 2 periods, just like in Python. In other words, these are equal. So from 0 to 2, you can write as from nothing to 2. These are the same. You can omit the 0. And if your slice includes the last byte of the string, you can drop the trailing number as well. So if you want to start from the third index character or byte and go to the end of the string, you just don't put anything here, which is good for convenience. Or you can put slen, basically the same thing, but putting nothing might be more convenient. Okay, you can also drop both values to take a slice of the entire string. So these are equal. I don't know why you would want to do that though. If you want to take a slice of the entire string, you can just not put any values in the range. Or you can put a 0 and len. You need to define len as slen though. I wish they just put slen here. This is kind of confusing. People are going to just put len here. Beginner programmers. But then Rust is not for beginners now, is it? Okay. String slice range indices must occur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. For purposes of introducing string slices, we are assuming ASCII only in this section. So that means 1 byte equals 1 character. But with UTF-8, I think it's 4 bytes. A more thorough discussion of UTF-8 handling is in the Storing UTF-8 Encoded Text with Strings section of Chapter 8. Okay, good to know. With all this information in mind, let's rewrite first word to return is slice. The type that signifies string slice is written as &string. Okay, so that's the return type. Let bytes. Okay, let me just type that. Not usize, but &string. And then if item is the byteified version of a space character, turn the slice. Nice. Turn the slice from 0 index to the ith index, not including the ith index itself. Otherwise, return the entire string sliced. So reference to the string, I guess. Something like that. Not sure what the difference would be of doing this versus doing that. I mean, isn't this the same thing? Anyway. We get the index for the end of the word the same way we did in listing 4-7 by looking for the first occurrence of a space. When we find a space, we return a string slice using the start of the string and the index of the space as the starting and ending indices. Right. Now, when we call first word, we get back a single value that's tied to the underlying data. Right. So this function is coupled to this parameter. The return type is based on the data itself, right? You're returning a reference to that's a slice of the string that's being provided as an argument to the function. So it depends on your return. These returns depend on the string itself. Returning slice would also work for a second word function. They not only depend on the string, they return a pointer to an address, to an index of the string, right? So that's the kicker here. You're not returning a new object in memory from the function. You're returning an address that's associated with the string that's provided. That will also work for the second word function. We now have a straightforward API that's much harder to mess up because the compiler will ensure the references into the string remain valid. Remember the bug in the program in listing 4-8 when we got the index to the end of the first word, but then cleared the string so our index was invalid? That code was logically incorrect, but didn't show any immediate errors. So that's important with any programming language. Okay. The problems would show up later if we kept trying to use the first word index with an emptied string. Slices make this bug impossible. Let us know we have a problem with our code much sooner. Using the slice version of first word will throw a compile time error. Yeah, nice. Let me get this in there. It's clear and line. And cargo run. Yeah, local variable with a similar name exists. Oh, let's do that. Okay, now mutable bar occurs here. That's the error. It's the same error. Mutable bar occurs here. Recall from the borrowing rules that if we have an immutable reference to something, we cannot also take a mutable reference, because clear needs to truncate the string. So it needs to do some operation on the string that's apart from reading data from the string, right? Anything that's not reading data requires a mutable reference. It needs to get a mutable reference. The print line after the call to clear uses the reference in Word. So the immutable, so here, this thing. So the immutable reference must still be active at that point, right? This is the immutable reference, and you're trying to use that. But in the meantime, you got a mutable reference to the string. Rust disallows the mutable reference in clear and the immutable reference in Word from existing at the same time, and compilation fails. Not only Rust has made our API easier to use, but it has also eliminated an entire class of errors at compile time, which is important. All right, string literals as slices. Recall that we talked about using string literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. The type of S here is &string, so a string reference. It's a slice pointing to that specific point of the binary. This is also why string literals are immutable. &string is an immutable reference. String slices as parameters. Knowing that you can take slices of literals and string values lead us to one more improvement on first word, and that's its signature. A more experienced Rustacean would write the signature shown in listing 4-9 instead, which is this, because it allows us to use the same function on both &string values and &str values. Okay. By using a string slice for the type of DS parameter. Okay, so that's a string slice type. And that's a string reference. This is a string slice reference. Gotcha. I'm wondering something. Would the compiler complain? All right, let's not do mutable. If okay, it's not complaining. If I did this, return &s here. No, it's not complaining. It's just, S is a string reference. What if I try to return this S? What then? It's still not complaining. So there's some interesting things going on there in terms of types. Okay. If we have a string slice, we can pass that directly. If we have a string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of deref coercions, a feature we will cover in implicit deref coercions with functions and methods section of chapter 15. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. Main. Okay. Let my string be a string from hello world. First word works on slices of strings, whether partial or whole. Okay. First word also works on reference to strings, which are equivalent to whole slices of strings. So that and that are the same thing. Okay, my string literal is hello world. First word works on slices of string literals, whether partial or whole. Okay, because string literals are string slices already, this works too without the slice syntax. There we go. Interesting. String literals are string slices. String literals are string slices. Interesting. So this is &str. The type of this thing is. Very, very interesting. Okay. String slices, as you might imagine, are specific to strings, but there's a more general slice type too. Consider this array. Let A be this array. Just as we might want to refer to part of a string, we might want to refer to part of an array. We do so like this. Let's slice &A index 1 to index 3. What is that? This slice has the type &I32. It works the same way as string slices do by storing a reference to the first element and a length. You'll use this kind of slice for all sorts of other collections. We'll discuss these collections in detail when we talk about vectors in JEPRAID. So collections are sequences, basically. They can be ordered or unordered, maybe. I don't know. What is that? I don't know what that is now. Assert equality, maybe? The concepts of ownership, borrowing, and slices ensure memory safety in Rust programs at compile time. The Rust language gives you control over your memory usage in the same way as other systems programming languages, but having the owner of data automatically clean up that data when the owner goes out of scope means you don't have to write and debug extra code to get this control. That's the one of the main great ideas of Rust, I think. Having the owner of data automatically clean up that data when it goes out of scope. Ownership affects how lots of other parts of Rust work, so we'll talk about these concepts further. Move on to chapter 5. Structs. Okay, we'll continue on in the next part of the series.